Welcome, class. We are talking series and sequences again in Unit 1. We'll be talking about geometric series. We'll talking about convergence and divergence of infinite series and how to test if they converge or diverge with the nth term test, the integral test, and the p-series test. Oh, that's a lot of stuff today, but I'll tell you when to really record. If I circle things in red boxes, that's important to write down because you're going to get a bunch of these tests for different series over the next few lessons. And those are going to be important to save. I know it's a lot of things. You're like, why do I need to memorize all this? What's going on? Where's the derivatives and integrals? This is BC. You're in BC land. We go in crazy places right now. This is one of those. So sit back, get your thinking caps on. Let's begin. So we've talked about a sequence before, and in this warm up we just did right now. These were sequences of numbers. Ignore number 2. Pretend I didn't write that down. These are sequences of numbers, and why are they a sequence? Because they are. It's just like a list. So if I was in programming right now, I'm talking about a list or an array. It's just a list of numbers. They probably follow some kind of pattern, and that's what we're looking for a list when I do a sequence of numbers. And maybe they keep, infinite sequence of numbers keeps going up forever or whatever. So that's a sequence. But we're going to talk about a series. So the idea of a series, the difference is it's adding all those numbers in the sequence together. All right. So it's not just, okay, going 1, 3, 5, 7, etc. It's I am now, or going up to infinity, I am now adding all those numbers together. So when we talk about series, we have this notation right here. Sometimes we call this notation summation notation or sigma notation. Summation or sigma notation. And we have this like E looking thing. I think that's actually the sigma sign in Greek or Latin. I don't know. One of those two. Look it up. So a few notes on that notation right here. You have a few key parts. You have right here is going to be your formula. I'm going to say that's the formula. Probably want to write this kind of stuff down. And then down here, we're going to have like n equals 1, typically a number like right here. This is where we start. Your starting number. And then on the top is where you finish. So we're going to finish for the end. So this will be the formula you use, and your starting number would be the starting number you plug in for the variable in that formula, and this will be your final number. Now, typically when we do these problems, the starting number is going to be either 0 or 1, usually when we count. And sometimes the finish could be going to infinity, or it could be a certain number. I want to do it for example over here on the side. What if I said sigma notation, and I said my formula was like, I don't know, 2n plus, no, I don't want to just copy that other one. What if I said sigma notation, and it's going to be n squared from n equals 1 to 4. What that means is I start with n is our variable in here. Now, why are we using n instead of x? I don't know. That's typically, instead of using x for these series, we typically use n's, but it could be an x, something else. So this means I start at 1 and go to 4. So it'll be 1 squared plus 2 squared plus 3 squared plus 4 squared would be this in sigma notation. So it's 1 plus 4 plus 9 plus 16, which would equal whatever that is right there, 20. That's going to be 30, I believe. Yep, 30. Okay, that's the idea with sigma notation. We're adding those up. So if this was like a pre-calculus class or introduction to sigma, maybe you have like your starting number and your ending number. It doesn't have to start at 1. It can start at 0. Sometimes they do. So again, whatever. Now, in calculus, we're going to be talking about these series. We're really talking about infinite series. So what if they kept adding numbers up forever? Adding more and more numbers, right? Well, what happens when we go up forever? So more and more numbers. Let's say if you took that series like this n squared series. The next one, if we went up, what if I did n squared? The next one would be 5 squared and 6 squared, 7 squared. If I kept adding numbers, we're going to infinity in these cases. These numbers keep getting bigger and bigger, and I'm adding to it. So it's going to infinity. Like, and taking this case right here, this is 2n plus 1. So the formulas, and you're starting at 0 in this case. So your first number would be 2 times 0 plus 1. And the next number would be 2 times 1 plus 1. And 2 times 2 plus 1, and so on. So this 2 times 0 plus 1 becomes 1, times 3, and this is 5. And then the next one would be 2 times 3 plus 1 and 7, and so on. If you kept adding more and more numbers, you go to infinity. What is it going to do? It's going to the moon. It's going to infinity. So that what happens when more and more terms of a sequence are added, a series are added like this? We're going to infinity. It's growing forever, right? In this case, it would be growing forever. These could be negative numbers too, and they could be just going down forever, right? And you might say, okay, well, these series will always just go up, go to infinity. Do they always do that? They don't actually. There's actually certain, you can write a series, an infinite series where you keep adding things, but they don't go to infinities. They go to a certain number, right? So what we're doing in these lessons is talking about, hey, what kind of series would add to a certain number? Wait, or is the series going to go to infinity and diverge, or is it going to go to a certain number and converge to that number? That's the heart behind a lot of these lessons. All right. So, okay, ignore that warm up. Who cares? So let's take an example right here. I hate this example. I'm going to make up a new one. What if I had a different series? I'm going to have a series. What if I had a bunch of 1/2s to the n power? Just like this. What if I start at n equals, let's go at n equals 0 to infinity. Let's write out, what would 1/2 to the n power be? Well, it's going to be 1/2 to the 0 power, 1/2 to the 1 power, 1/2 squared, 1/2 cubed, and so on. You actually wrote those out. 1/2 to the 0 power is 1. 1/2, this is going to be 1/4 plus 1/8. The next one would be 1/16. You can follow this pattern and so on. If you actually added these up, so let's actually make this, I want to make this as a number line to kind of show you what's happening. If I had a number line, I'm going to try to make this even. Oh, gosh. Eyeball this pretty even. So let's treat this as a number line, and we're just going to keep adding chunks. And what's going to happen, let's say, so this is 1, 2, 3, and so on. If you added 1, that's going to fill you up to 1. And now I'm going to add 1/2 to that. That's going to fill me up to be at like 1.5. Well, what if I added 1/4 to this? Well, that's 1.5 plus a fourth. Get me out here, which is about 1.75. And then what if you added another 1/8? 1/8 is going to be, you add a 1/8 to this, 1.75 should get you halfway between 1.5 and 2. 1.7, if you add a 1/8 to this, you're actually going to get you about halfway there, and you get to like 1.825. I believe there's that one. Trust me there. That's right. No, 1.875, right? 875 is the answer. Close enough. Okay, what if I added the next number? You see, it's going to get me half my distance to 2 every time. If you kept adding these numbers up, it's going to give me half my distance to 2. And in fact, all right, so I was trying to pull up a graphing calculator here. So here's my table and my y equals equation, 1/2 to the x. Pull up your table, and here's what I'm adding every time. So if you didn't trust me on my math, so my next one, I'd be adding 0.3 to this. Basically, every time I'm going to add a bigger number, it's going to add half that distance. What if I kept doing this to infinity? You'll notice here, I actually approach the number 2. If you kept doing this so if you do an infinite series right here, you're always adding a little bit more. It's always getting a little bit bigger, but it's going to approach the number 2. It's getting infinitely closer. It'll never actually reach 2, but it'll always be adding a little bit more. So this would be an example of a series that would converge to a number. In this case, we converge to 2. So there are series that will converge, even though they're adding something all the time. So I show this to you, kind of show that off. Now, let's go back to this lesson. What if I did this one? 3 over 10 to the n power. What happens when more terms are added for this? So notice it's only 10 to the nth power. Okay, So if I did this one, I'm going to pull it up on a graphing calculator right here too. What if I made my formula? It's going to be 3 divided by, oops, 3 divided by 10 to the x power. Wait for this. Okay. Only 10 being powered. So I'm going to go to this table and watch what would happen. These are the numbers I'm going to be adding right here. Write this down. Yeah. So your numbers are going to be 0.3 plus 0.03 plus 0.003 plus 0.0003. What if you kept adding these? I mean, notice these if I just added the column. If you kept adding these numbers, that's gonna equal 0.3333, and it keeps going on forever. As a decimal, if I have repeating threes, what's that as a fraction? You might know this right now, and that's the same thing as 1/3. So this infinite series is going to actually converge to 1/3. Now, all of these series and that converge in this case, this is not red yet. This is what we're going to call a convergent, a geometric series. When we have this like exponent to the nth power here, we're going to be calling these geometric series. And in fact, here's the part I need you to write down. Here's your geometric series. I'm going to pause the video. Key parts right here. So a times r to the n. And here's how it would expand out. So you have your r is being to the nth power. So whenever you see this nth power, the variable, that's your key. It's a geometric. So an example could be like 1/2 to the nth power, where, okay, so your a, sometimes we call this the first term, and the r is the ratio. So this only works is the first term if n is starting at 0. Not always. That's just a coefficient in front. So this geometric series will converge. It's all depending on the r, this ratio. If that r absolute value is greater than 1, we diverge. If it's less than 1, we converge. So for example, when I had 1/2 to the nth power in that previous thing, our a in this case, and what's our r? Well, r is the 1/2. It's that ratio right here, right? Our a, there is no a. It's like an invisible a. It's like a 1, 'cause 1 times that, okay? So in this case right here, our r is 1/2. Since the absolute value of 1/2 is less than 1, it will converge. And as we saw when I did the math before, we said it converged to 2. Okay. Now, I can make up another problem here. What if I had 5 times negative 1.05 to the nth power? Well, you look at what's my a in this case. It's going to be 5, and your r a is just a coefficient, whatever. And the ratio is negative 1.05. Well, the absolute value of this 1.05 is greater than 1, so that would diverge. Your ratio that in here needs to be a fraction between -1 and +1. Another way to see this, I hate, if you don't like this absolutes, I like doing this as a number line. Maybe that helps you out. So I'm going to do a number line. And I'm going to do it over here. So -1, 0, 1. You had it like this. We are between these. Between those two, we converge. Outside of those two, filled in, when it equals that, or over here, we diverge. Maybe you want to think of it like a number line. Between -1 and 1, we converge. All right? Now, geometric series has a unique thing that I can figure out what does it converge to. Converge to what? If I know it converges, I can actually tell it what it converges to with this formula. A over 1 minus r. You might have seen this in algebra 2, but probably not. I remember learning some algebra. Sometimes it's taught in that, but I think it gets skipped over. I don't know. Common Core, maybe it messes it up or gets forgotten. So a over 1 minus r is what it converges to. All right. Where a is your first term And then now, and then R is the ratio. Now, when I say first term here, this is assuming n equals 0. If n equals 1, then their first term is A times R. So I hate that, but usually just the coefficient. A few other things. A question was asked, what does diverge and converge mean? Converge means it goes to a number. It goes to a number. It's going to add up to a number. Diverges means it's going to go to like infinity or negative infinity, or it's going to oscillate. So maybe it like rotates between converges and maybe it like rotates. And so something that would oscillate would be the sum of -1 to the nth power, because that's just going to be like 1 plus -1 plus 1 plus -1. It's going to rotate between 1 and 0, but it never like approaches anything. All right. We'll get to inconclusive later. In these cases, we don't have inconclusive. All right. So let's go back to, so if I did this problem right here, right? And I want to say, does it converge or diverge? I said it converged. How do I know I did the math with a table to prove it was 2, but let's say I followed this formula. My A in this case is 1 and ratio is 1/2. So the sum, sometimes we do like S for sum. Sometimes we say this is sum for S, is going to be A, which is 1 over 1 minus 1/2, which is 1 over 1/2, which is the same thing as 1. I like, instead of divided by a fraction, multiply by the reciprocal. Going to be 2, which is what we figured out with the math that we did. Now, I can even go back. Remember this one? Let's say you had this sigma notation right here. And in this case, now my R, okay, so the trick is your R is not 3 over 10. I want to rewrite this one. It's 3 times 1 over 10 to the nth power. Because only 10 being exponent. So in this case, my R is going to be 1/10. My A, which is my first term, is actually going to be, it's 3 times, since I start at n equals 1, they're going to be 3/10. That's really annoying. I hope we don't start at 1 a bunch. So if I wanted to find the sum, and I know it converges because my ratio is 1/10, it's going to be 3 over 10 divided by 1 minus 1 over 10, which would give you 3 over 10 divided by 9 over 10. And I'm going to rewrite that as, not that color, as 3 over 10 instead of times 9 over 10, reciprocal 10 over 9. Those 10's going to cancel. 3/9, which is equal to 1/3. So it's still worked out. So I don't have to use that table method. I can use this formula for geometric series. What's weird is geometric is the only series that you can actually find the sum for. The other ones, I don't have a formula for, as you'll see. All right. There's a lot going on there. We're 18 minutes in, but I ain't done. Other questions? All right, we're on to the next one. We're going to go to the nth term. So that was geometric series. Now we have another type of series here. We're going to call the nth term test for divergence, and you're going to write this down. So because every series is not a geometric series. This is another type of test we use, all right? And this is like the most generic one. We call it the nth term test. And it says, nth term test for divergence. If the limit of that function is not equal to 0, then the series if the limit's not equal to 0, the series diverges. The test is inconclusive if the limit does equal 0. So write that down. So in this test, if the limit of the formula in here is not equal to 0, it's going to diverge. It's inconclusive if it equals 0. So this is the idea that to add for a series to converge, it has to go to a number. That means like the magnitude of the numbers you're adding up has to get smaller as it goes out to infinity. If those numbers are staying the same size, this is kind of like the default test, the first test to really use sometimes. Like if you don't know what to do, maybe see if this diverges. They give this example of this formula right here: 1 plus 1 over n. So this would be like, well, so let's do the limit of that right here. If you did the limit of this one, I'm going to write it over here to the side. It doesn't matter where n starts. All I care about is n going to infinity. So I'll check the limit as n goes to infinity of 1 plus 1 over n. Well, that'd be like 1 plus 1 over infinity, which is 1 plus 0. So it's just going to be 1 in this case. The limit goes to 1, so it will not converge. We say it diverges in that case because 1 is not equal to 0. Now let's take another case. Let's take the problem we just did. What if I had 3 over 10 to the nth power and I applied the nth term test to it? The limit of 3 over 10 to the nth power as n goes to infinity would be 3 over 10 to the infinity is 3 over infinity, which is 0. Because this is 0, our test is inconclusive, IDK. That means I have to use a different test, and in this case, I would use geometric. Now, it doesn't mean that they're not always going to be, now this, we know it converges. But here's a case of something that wouldn't converge. What if I did? Okay, no, I don't want to do those other things yet. So that's idea, nth term. So I hate that example with factorials. Don't do that to me, bro. We're not going to do that. That's the idea. Nth term is about what's the limit as you go to 1 or go to infinity. I'm going to add another test to this. Integral test. Oh, there's no red box around this. Well, guess what? Put that red box around it. No. There you go. Write this down. Integral test. So if a function is positive, continuous decreasing for greater than 1, they either both converge or both diverge. So I say this in my words: if you can integrate it from 1 to infinity, if it converges, remember we talked about converging, it goes to a number, goes to a number. Not it converges. So if it goes to infinity or negative infinity, we say diverge, right? Just like we did for those integrals. I hate this test, least useful, because I think it's too much work. And you're never going to you're only going to use this if you have to. Trust me. The weird thing here is, what does positive continuous and decreasing look like? So that would be a function. A function doing this would be that. Positive means we have to be above the x-axis. Continuous means pencil test, right? And decreasing means it has to be getting smaller. You're looking at a function that's above the x-axis getting smaller. Because remember, it, like we said with nth term, they have to be, as you go to infinity, this has to be going to 0. So it is going to be smaller, but it has to be positive. Why can't it be negative? Why can't we like down here and go up? I don't know. So, okay, that means we integrate this. Great. Well, what's a for example of that? Hopefully you got this. Here's a for example. What about this one? If I looked at this. Okay, so the first thing you might try is nth term test. Okay. You try the limit as n goes to infinity of this thing of 1 over n times ln of n, right? That would give you 1 over infinity times ln of infinity, which is 1 over infinity, which is 0. That's inconclusive, so IDK from this test. All right. Then I have to use another test, and I go, oh, let's try integrating this. I'll integrate from 2 to infinity because it says 2. So we're going to integrate 1 over n times ln of n, dn. You're like, oh, how do I do this? It's a u sub problem. Your u in this case is natural log of n, du. would be derivative of ln of n is 1 over n dn. And the way this class works, you want to isolate the dn, so I times by n on both sides, is n du. So I plug that in for dn, so I go n du, and 1 over n times u down here from this and this. And then those n's cancel out. Go of 1 over u du, which ends up being ln of absolute value of u from infinity to 2. So it's ln of infinity minus ln of 2, infinity minus a number. We diverge. This function actually diverges here, folks, because we have this infinity. So in this case, we would say it diverges by integral test. So notice nth term was inconclusive. Just because it went to 0, it doesn't mean it's going to converge. We have a case where the limit goes to 0, but it's going to diverge by integral test. This actually, what's weird is like these numbers, this number is going to be like adding a little bit and it gets smaller and smaller and smaller. But which is frustrating. Sometimes it's frustrating to me. It's like, well, it's getting smaller. You're telling me it's just getting smaller, but it's not getting small enough that we can say it converges to a number. Like, why does this still get, I don't know. So, like, that blows my mind sometimes. And that's frustrating. Yeah, I can do another integral test. Please say I can. Yes, I got them right here. I'm going to do more integral tests. I'm actually going to rapid fire these right here. All right. So let's do this 3 times because this is relevant to the next lesson. 1 to the infinity of 1 over n. These ones are easier, right? So integral of that is going to be natural log of n from 1 to infinity. I don't do that limit thing. It's too much to write. Ln of infinity minus ln of 1, which is 0, but that's just going to be infinity. So this is going to diverge by that limit test. Let's say if I did this middle one right here. Okay, so that's the same thing as integral. This is like n to the negative 1/2 power. Why is it my hand? What's with my writing right there? Ugh. Shaking too much. I'm too excited. Got to calm down. So if you integrate that, you have to add 1 n to the positive 1/2 times 2 over 1 from 1 to infinity, which is going to be 2 times infinity to the 1/2 power minus 2 times 1 to the 1/2 power. But that's still infinity right there. We diverge. Do they all diverge? Find out. Let's do this last one. And do the one down here. We integrate from 1 to infinity of 1 over n squared, which is the same thing as integral of n to the negative 2 power from 1 to infinity. That's going to be n to the negative 1 over negative 1 from 1 to infinity, which is like negative 1 over n from 1 to infinity. We get negative 1 over infinity minus negative 1 over 1. This math right here is going to be 0 plus 1. So it equals 1. So we actually converge, in this case, by the integral test. Now, it doesn't converge to 1. Okay? This is not saying that it converges to 1 if you added that series up. It's not the same thing because, and think about this, like an integral is a smooth curve. When I do a series, I'm doing like Riemann sums. It's a bunch of rectangles. It's 1 is probably a good approximation, but it's not going to be the answer. So here's 3 cases. Yeah, it's a lot, but the Khan Academy is not too bad. It's all multiple choice. Yeah, and I know. Like this can be gross. Like it's a lot of new things at once. You're like, why? Why are we doing this? You're like sitting there going, why these formulas? WTF? There's a lot of WTF in this. All right. Now, integral test is the grossest thing in the world. But I'm going to show you something that's easier. The final one for today. The P-series test. Red box. Pausing this. I'm going to record. The P-series. The idea of P-series is we have, you know how we had like geometric had n as the exponent? P-series is n is the base. Okay, n which is our variable. Geometric series is the exponent, n is the base, and p is just some number. P is a positive constant number. It could be a decimal, positive number. Then we'd write the series. So if I had an nth to the, so it might be a series 1 over n squared, or series 1 over n to the 1.1. Or you could even put a number on top. I could put like a 3. Let's not worry about that kind of stuff. But it's just n to the whatever power, called the P series. And it converges if P is greater than 1 and diverges otherwise. So a number chart, bigger than 1, we converge, less than 1 or equal to 1, we diverge. So for example, if I had 1 over n to the 1 power, or just 1 over n, we would diverge by P series. This is the most used test as a base for some other things too. So if you like this chart, great. I like to think of it this way in my head: bigger than 1 converge, less than or equal diverge. You might be like, well, why is this say from 0 to 1? That's what tripped me up. Why not -1? Well, if you had like 1 over n to the -1 power, that's just same as 1. That's just n. And this is going to diverge by the nth term test. That's why they say this 0. But really, you could just dump the 0 and just say less than that, because it'll diverge by P series. Doesn't matter. I don't know why they limit it. It doesn't matter. So guess what? Remember these guys? I'm going to take your work. I'm going to take this. I'm going to erase it. Remember all this? We had to do this integral test. Now we're going to apply P series to this. P series. Take this first one. Why is my phone doing that? 1 over n. In this case, my P equals 1. And that means it's going to diverge. This one. That's 1 over n to the 1/2 power. My P equals 1/2, which is less than 1, less than or equal to 1. We diverge. This case, my P equals 2, which is greater than 1. We converge. Yeah. P is your exponent to the base. If n is the exponent, P is whatever power it's being done to. That's how you get P. So this is like n to the 1 power. This square root is like to the 1/2. That 2. There was a question of what if we had 3 to the 3rd power, or like an exponent like 2, or other numbers in here. We're not going to get into that. That's going to be what we get into next time in class, which is Thursday. But we're also going to get into something else right here on Thursday. John Smith subs. It's a fundraiser Thursday. I hope to see you all there. They're really good. That's the lesson.